Hello everyone. In this video lectures, we are going to learn early effects, and we are going to incorporate early effects into the pi model, the small signal model. The next thing that we are going to do is to run an example based on the small signal model that has the, that has the early effect. So before going forward, right, let's recall what we have learned. We have learned the symbol of the transistor, and we know the voltage VCE is here, and the current IC, and we have the base, and we know the voltage VBE. And if we plot the characteristic IC and VBE, we will end up with a characteristic somewhat like a diode. And the voltage here will be 0.7 volts. And at the time when the Bell Lab scientists discovered this device, they found out this curve and they try to vary the voltage VBE, and they found out at different so they try to vary the voltage of VCE, and they find out the curve, the slope of the curve will be different. So the higher the voltage VCE, the higher the collector current they will get for each VBE. Uh, there's not much you can do for this graph. Uh, then they play with the circuit, and in the hope that they find out eh, more detail about the device. And accidentally, actually not accidentally, they found out originally they used the device for verification, which is good. They can use the PE voltage to control the current of the other branch. Um, but this is not good enough. What is more is they try to plot this IC against this voltage. So essentially, they are treating this as a um, resistor. And surprisingly, they find out something like this. The curve in this region is almost, the slope at this region is almost zero. And this is the ideal case. So this is a very, very phenomenal discovery. The uh, region here is flat. At different value of VBE, you end up with um, a complete flat line in the active region here. For instance, the VBE here is just 0.5, and VBE here is 0.6. VBE here is 1 volt, for instance. And this is how they managed to further their analysis and further their discovery. The device is not just an ordinary transistor, ordinary resistor. This means no matter how you change the voltage, CE here, the current will remain the same, flat. There is no change in current at all. But this is just the ideal case. So what is not ideal? The not ideal one is here. Originally, you want it to be ideal. This means originally, you have something flat in this region, very, very flat. I'm sorry, I should draw the graph in here. I don't have enough space there to analyze it. So, um, E, C, E, and then I, C. And what they get is, they still get something similar to the original one. But with higher CE voltage. They end up with something like this. So in other words, uh, unlike the ideal case, in the ideal case, no matter what sort of voltage you have in VCE, they have a so-called the effect, the early effect, and this is the non-ideal effect. And the higher the CE voltage you have, it's just like a resistor. You end up with higher current, higher collector current. So in other words, uh, the real discovery they have done is the one with non-ideal situation, where um, there is a something called early effect. Early is the surname of the scientist who discovered this effect. So if your Q point is here, you want to claim this IQ, ICQ. The voltage at this point is VCEQ. And the actual current that you are measuring is higher. So this will be your current, ICQ. So how about this current? This current is the ideal one. The ideal one, let's say IC naught. So IC naught is the collector current. IC with low early effect. And IC, yeah, I'm not going to call this ICQ because it is getting more confusing now. Let's call it IC. And IC is the collector column with early effect. So at that time, early was a scientist who discovered this effect. And he didn't call anything like this. He didn't specify any variable with his name or surname. Instead, he just do something very simple. Um, he extend this slope region. So we are now dealing with this one. He extend it. So he end up with something like this, and then he extend the horizontal axis as well. So at this point, the voltage is VCE being equals to 0. And at this point, VCE is equals to VA. And I don't know why he chose to use VA. Um, VA itself is early effect voltage, early voltage. Now, with this in mind, then we should be able to separate we should be able to come up with an equation, a formula for IC in terms of the ideal collector current and early voltage. And let's see how we can do. So the ideal one should be forgotten now because nothing is ideal in our world. And this diode line characteristic is also not applicable in these lectures. And the symbol here might be useful, but not for now. And we are going to analyze the early event. So basically, you have two columns here. The original one is IC0. The new one is IC. The new one, IC, is the non-ideal one as a result of the early event. The non-ideal one is much higher. And uh, let's analyze it. So how do we go analyze it? What Early has done was he identified this large triangle and these smaller ones are similar with each other. So if you consider the smaller one first, I C naught divided by VA. Consider the two similar triangles. And we can say when I C naught divided by VA. And if we look at the larger triangle, we have IC divided by, if you just count the length of this larger triangle, you will know that it is VA plus VCE. So if you want to find the value of IC, then it will become IC naught divided by VA. And obviously, IC naught is equal to 1 plus VC naught over VA. And if this is the case, then you can also write IC. You can express IC as a combination of two components. And plus this one here, IC naught divided by VA and then VCE. So now basically you can just rearrange this term and VCE, and the bottom value is VA divided by and at that time John Early called this term analog, which is so-called early resistance. So if you are going to represent this into a model, then it will be like here, a diode, and then a current source, and the current source is the IC naught. And so this is the last signal model that you want for the early effect. But of course, the last signal model is not going to be enough for you. We want to know the small signal, the small signal model. So what we can do is we do further analysis based on this. What we can do is to differentiate this equation. Suppose this equation is equation 1. So if you differentiate equation 1, you get IC and then IC naught, and then the bottom term is assumed to be constant, because in effect when you draw the graph, the IC naught is not changed. So we assume this bottom term constant. So we see E here. Or equals to IC, right? I told you before we can use the small letter to represent it. And then, the bottom expression should be R log. And the R log is equals to VA divided by IC log. And this is the equation for building a small signal model. So suppose that you have a small signal model like this. This is what we have learned in the previous lectures. And now you have one more term here. And this term is proportional to the voltage, CE. So you have a term, resistance term here. And this is so-called early resistance. And this is the so-called um, IC, sorry, and this one is IC naught. IC naught is equal to GM over V pi. So this is the model that we need for calculating the amplifier circuits. Now, you have got this model. Perhaps you might also want to know the physical reason why we end up with early effects. And in the lectures, I have skipped this part. The students from the previous intakes know well what the exact reason is because they have done physical electronics. But you guys don't. So I suggest you just memorize the reasons. Just in case in the coming future when you are interviewed for jobs on IC design, when you are asked a question about the early effect, at least you know what caused the effect here. So I told you the early effect will end up with higher collector current, and the reason is very simple. Now imagine if you write the transistor in as a free sandwiched region. So we have N, P, N. And the region here is E, C, B, and E. So uh, we have the VCE higher, and we end up with higher IC. And we want to explain why in terms of early effect. The reason is when with a higher VCE, you have a larger region, the division region here, the thicker division region here. And thicker division regions mean thinner base. And thinner base means less chance of hole and electrons recombination. And in physical electronics, in semiconductor physics, um, less chance of hole electron recombination means higher collector current. So I hope this is clear enough for you. if you are interested in this topic, right, I can explain this to you further. You just ask. If you are not interested, you just forget about this. If I need to ask this question in the examination, I will tell you first. Okay? So I'll give you 1, 2, 3. Okay, you can raise it. Now, the next thing that I would like to do is to show you how to apply the model in our circuit analysis. And suppose we have an example. In example, we want ROC to be, we want RC to be, say 1K, and VCC to be 10 volts. And we also, we don't know the collector current. And we want a very simple circuit. The simple circuit is just like this. So for example, right, we know this model and we don't erase it. Right, so the circuit is here. And you have a resistor RC. So if they don't specify the collector current, this means you are the one who need to find out the collector current. And I have already told you the maximum collector current is, yeah, we can just we draw, we learn, recall what we have done. So if we plot the equation here, ICRC is equal to VCC minus VCE. So IC is equal to minus VCE divided by RC. VCC RC. So this is the so-called low line. Low line. And based on this low line, we can find the x-intercept and y-intercept. The y-intercept here is VCC over RC. And of course, we want maximum strength and we want it to be little. And the current that we end up with here is VCC over 2RC. So this is the current we have got. VCC is 100. RC is 1K. Then we have 10 divided by 2 times 1K. The value that you get here is 0.05 ampere. So 5 microampere, 5 milliampere. So now, if IC is 5 ampere, then IB will be equals to, say, let's say beta is 200, just like 2M22, and the early voltage is 100. This is the very typical situation. Let's see, different model, they have different value for beta and early effect resistance. So bear in mind. We have IB here, and let's say we have another resistor here. And this resistor is up to us to determine. So IB is equals to VCC minus 0.7. Remember, this voltage is 0.7. So 10 minus 0.7, this is 9.3. And RB, we don't know what, but we know ROB is equal to IC over beta. And if this is the case, ROB is equal to beta times IC. And what is IC? We have already got it. So 9.3 times beta. Beta is 200. Yeah? 200. And we have IC. IC is this value, 5 milli. And we will do some calculation here. 9.3 divided by 0.05 times 200. So what we get is 372K. So we better write down this value here. And I think for now we have already done the DC analysis. And we are going to push further. And with this in mind, we have 0.05, so 5 million. And now everything become clear now. And suppose you don't need to, I'm going to erase this part. Yeah, if you need to, you just rewind the video and you check the value. And now we are going to do small signal analysis for this amplifier. Remember, this biasing network can be used for not just common emitter amplifier. And V in and V out. And remember what we have done. First, we need to replace the transistor with the pi model, which incorporates which is our pi, and this one is GM V pi, and do not forget we have a early resistance here. So this is the complete pi model. And the next thing that we need is to replace the independent DC voltage source as the AC ground. And this AC ground is not very much different from the physical ground here. So in other words, right, this vertical ground can be moved to here. And we can just write RC here. So we remove this one. And for here, we can say OP. And all the capacitor should be replaced with a short circuit. So this one is short circuit. So now we should know the almost everything now, right? So first, this parallel combination can be simplified as R naught, and this parallel combination can be simplified. And now we have basically almost everything. Now the next thing that we want is to calculate GM. Yeah, we need to calculate the voltage. Divide the voltage gain first. Uh, V out over V in. So what we do is to calculate the current at this point here. The current at this point is IC, yeah, IC, IC naught, right? IC naught, which is equal to GM and then V pi, and which is equal to minus V out divided by R naught. So what else? Um, you do just need to do some, and one is V bar. V bar is the voltage across this resistor, and V bar is the same as V in. So we base it as V in, and based on the information here, and now apparently, right, we need to know the value of Gm. Remember, Gm is equal to um, uh, IC divided by Vt, and naught, uh, R naught can be calculated, right? Uh, Va divided by IC, and if we substitute all the values here, um, we have minus 5 milli divided by 0.026, and uh, this value Va is according to here 100 divided by IC. IC is 5 milli, and RC is 1K. So if you do it carefully, let's see what we can get. Um, 0.05 divided by 6 times. It's around 19.23. 19. So this means the voltage gain is 19.23. And with this circuit, you should be able to come up with the current. So the next thing that I'm going to show you is to check this circuit. Is to go through this circuit in simulation, LT Spice. To as a circuit designer, uh, to before doing anything, you need to check whether the DC biasing is uh, has satisfied our design criteria. So in this case, because of our DC analysis, by doing this value, we find out IC is 5 milliampere. And this is exactly what we need to confirm. If we got 5 milliampere in the circuit, then this means our design is exactly what we want. And now the next thing that we need is to simulate a small signal analysis. And the end result of the small signal analysis is the voltage gain 19.23. And this value has to match, otherwise your analysis is not correct. So we are going to do it now. So to begin with, we open a LT SPI window. So I'm going to share with you the screen for LT SPI. So everyone can look at the LT SPI window. So you open a new schematic and say you have a NPN transistor. We pick this one. We pick an NPN transistor with exactly the same characteristic. And the characteristic in this case is beta is 200 and early effect voltage is 100. So we just pick this one, 2 and we put a resistor here. The resistor here is going to be 1 milli, 1000. The supply voltage the voltage here is 10 volts. So we just it a little bit further to the right. And do not forget the ground point. In LT SPI, without a ground point, the circuit will not be, the simulation will not work. And now the next resistor is the calculator one. And with this calculator resistor, we will end up with an optimal Q point and 372K. The very first thing that you need is to check whether the IC is the right value. And you can do this with operating point analysis.ob. And we simulate this. And indeed, the current that we get is 5 milliamp, which is exactly the same as what we got by calculation. So the first thing is done. We have got the satisfactory DC biasing network. The next thing that we need is to connect the circuit. We complete the design. We just need the input and output. And you need the input voltage. The input voltage is the voltage source, but the voltage source has the AC value. By default, you ask for the DC value. But this is not what you want. You want an AC value, the AC amplitude. And the value here should be 10 micro. Yeah, you just insert 10 micro here. And you are going to say 10 micro, 10 micro for the capacitor. And of course, you need to label the output. Do it again. Now the circuit is already available. You need to specify the simulation parameter, the simulation setup. What we need is the small signal analysis, where we can calculate the linear voltage gain. The small signal analysis in LT-SPI is called AC analysis. And in the AC analysis tab, you select the type of strap, and I personally prefer decade, and the number upon 100, and the starting frequency at least 1 Hz. The stop frequency can be any value that is large enough. I will just use 100, 1000 K. So if we simulate this, if everything is correct, then you will immediately end up with a waveform window. And in the waveform window, you right-click it. Right-click your mouse. You have several options. The first option that you need to pick is add trace. And the next thing that you need to do, I forgot to label the input voltage. We need to label it. So we have two voltage, right? Output and input, and we put a backslash here, which means output voltage divided by the input voltage. So this is the body part, the part of the voltage gain, magnitude, and phase against the frequency. And it's difficult to read at this stage because you have not learned anything about decibel. But then you can also position the cursor in the vertical axis and change this to linear scale. And then this is what you are going to get. Sorry. Let's do this. So the voltage, let's do the, I think this is correct. This is good enough. Output over input. So now, if you take a look here, the voltage gain is about 180. This is not what we originally expected. Perhaps there's something wrong with our calculator. Let's see. 0.05 divided by 0.026 and then times 1 over 0.05 divided by 100 and then 1 over 1. Okay, the y value I have got is 128. So this is exactly what we have here. The voltage gain, right? At least is similar. So that's all. If you have any question, yeah, let's before going forward, let's remind you. The voltage gain I have calculated here should be equals to 128. And this value is similar to what we have in the simulation. So I hope this lecture is enough for you. If you have any question, please leave your questions in the comment sections of this video. Thank you very much for your attending this video lectures. Thank you. Bye-bye.